Welcome back. So, in the last class, we actually discussed about electric charges and how we actually uh, can talk about the force between electric charges and how it can be defined uh, more quantitatively using uh, Coulomb's law. So, how did Coulomb do it? All that we discussed in the last class. And now we are going to basically look at the charge base due to the force due to multiple charges. We have actually calculated if there are two charges given. Coulomb law tells us how to calculate, and we also figured out the vector form of that. So once you figure out the vector form, now we can actually say that we can find out the force because of the multiple charges, because we know that the forces can be added vectorially. So how do we do that? Let's just take, for example, a situation of two charges. Okay, two charges are there. Let us say this is charge q1 and this is, let us say, charge q2, and another charge is there which is, let us say, q3. There are three charges here. Okay, so always we took two charges to start with. Now there are three charges. So where are they? So let's say this is my uh, coordinate system, and let us say this is my origin O. Okay. From here I can actually draw lines and find out the position vectors. So the line drawn from here to the point is basically position vector, that is a vector, and that vector can be specified using ijk coordinates and all that. Okay, so that you all know. So this is a vector, what we call vector r2. This is a vector r2. Okay, and from here if I draw a line to this is r1, and the line that is drawn to this one is r3. There are three position vectors. So now from these position vectors we can find out the vectors which are basically distance between them, relative position vectors. So if I say here this vector is r12, and the vector that is here is, let us say, r13. r12 is nothing but r1 minus r2, and r13 is nothing but r1 minus r3. All these minus plus I am talking about in the form of a vector addition and subtraction, which you will have to do using either the ijk values, or you should use using parallelogram law. Okay. So now if you look at, let's assume that these are all positive charges. Now, the same logic applies for negative charges as well. So now from here, if you calculate basically what is the value of the force on q1 due to q2, let's say you will get a force which is F12, and that force F12 will be actually equal to 1 by 4 pi epsilon naught into, okay, q1 into q2 divided by q r12 square. This is the magnitude r12 square into r12 cap, which is basically the unit vector in this direction of r12. That is the unit vector in that direction. And how does it look like? It looks like here is basically a force which is, I will call it as F12. Okay. And similarly, if I write here, this will be F13. Okay, and F13 also can be easily calculated as 1 by 4 pi epsilon naught into Q1 into Q3 divided by R13 square into R13 cap. So this is basically the force on Q1 due to Q3. So now if I want to find out the total force on Q1, okay, we will say F1, the total force on Q1 is equal to F12 plus F13. So what do you write that? You will write it basically as this plus this. So I am going to take 1 by 4 pi epsilon naught as common. In fact, I am going to take q1 by 4 pi epsilon naught as common, and in this one I will be left with r12 cap divided by r12 square, and here also I am having a q2 here, plus you have a q3 here into r13 cap divided by r12 r13 square. So it is possible to actually generalize it for n charges. For n charges, if I generalize it, F1, the force on charge A1 due to other charges, you can say is F1 is equal to, I can say Q1 divided by 4 pi epsilon naught as is, and this one I add all of them. Okay, so sigma, you can see here Q2, Q3, next one will be Q4, next one will be Q5 like that. So if I take for example some variable I is equal to, that starts with 2 to n, I is equal to 2 to n, I can write down, and I can then say Qi into Qi divided by R, see here 1 2, here 1 3, 1 4, 1 5 like that. So 1 I square into R 1 I cap. So this is basically a general. So in the vector form, actually find out the force due to force on a charge due to multiple charges. So what we are doing here is that we know that it is very easy to calculate force on a charge due to multiple charges. Just a parallelogram law, multiple forces are there, you add them. But it is important to get a practice of doing so generically. Okay, like how you are going to basically, what is the general form of that? So you may be asked to basically derive force on a charge due to multiple charges in the vector form. So this is basically the proof for that. Okay. So now once you come to know about that, this will be very useful when we go into actually electric field. Okay, so now the same thing can be extended to the electric field. We will remember this particular statement, the final statement here, and we will come back to this when we are looking at electric field. So this is about basically force. Now let's do one or two examples, then you will come to know basically how it works. Okay, I'll take one example. Okay, so you can take down one example. I will just dictate an example to you. Consider three charges Q1, Q2 and Q3. Consider three charges Q1, Q2 and Q3, each equal to Q at the vertices of an equilateral triangle of side L. What is the force on a charge capital Q with the same sign as that of the small q, placed at the centroid of the triangle? Placed at the centroid of the triangle. Let me just try to write down that. So what you do is there is an equilateral triangle. And we have charges Q1, Q2 and Q3 placed at these vertices, Q1, Q2 and Q3. I will call this point as A and this as B and this as C. However, it has been told that all these charges are equal to Q only, is equal to Q, is equal to Q, is equal to Q. And we are supposed to find out, suppose if I happen to find out the centroid of this. So this is the centroid O of this, and at that point I am going to put a charge which is capital Q at O. Okay. So what is the force that is experienced by that charge? Now let's just look at this, okay, in the common sense viewpoint. Now, this since being an equilateral triangle and the distances AO, let's say this point is D. Distances AO, BO and CO are all same. So, they all are equidistant from this point, and they are all equal. So, hence the magnitude of the force basically will be equal to, will be equal in all the cases, because magnitude of the force simply depends on the charges themselves, okay, and also the, let's say I will call this as the magnitude of the force, okay, uh, F1, okay, will also be equal to F2, will be equal to F. Okay. What is that will be? That will basically be equal to the K into Q1, Q2, that is Q1 is in this case, everything is Q, small q, into capital Q, divided by, let us say the distance is AO square. This is the magnitude. Okay. So, how much is AO if we can calculate? We know these values. Okay. So, the AO is, let us say AD you calculate. Okay. This length is L, all of them are L. So, AD square is equal to AB square minus B square minus L by 2 square. Rather, this is L square minus L by 2 square. This is L by 2. So, this will nothing but L square. Then AD is actually equal to L into square root of 3 divided by 4, which is root 3 by 2 into L. That is AD. So, once you get AD, in the case of a centroid, we know that centroid actually is at a 1/3 distance from the bottom. This is 1/3 and this is 2/3. So, AO will be actually equal to 2/3 of AD, which is 2/3 of root 3 by 2 into L, which is actually equal to 2 cancels. So, L by root 3. L by root 3 is the AO. So, now you got AO as L by root 3, you can substitute here. Okay, how do you substitute? You start from K. Okay, now let's keep it as K only. K into Q, okay, into capital Q divided by L by root 3 whole square, which is nothing but 3L square here. This is the force. Each of those forces, that is F1, F2, F3 are all the forces that are acting on this at the point O on Q. So, that is the magnitude of them, but their directions are actually different. Let us look at which one is F1, which one is F2, which one is F3. So, both being the same positive charge, this fellow will push this. Okay, so push this means this will be in this direction. Okay, like this. This is F1. So, F2 will push this in this direction. This will be F2. And similarly, this will be F3. So, these are three forces equal and pulling at 120 degrees angle with each other. One can intuitively say that the force on this basically resultant force is equal to 0, or you can also actually calculate. How do you calculate? You will say, so look at this. This is actually, if you create a line, parallelogram here and do this. This is, I will call that as basically F2 plus F3. F2 plus F3 is equal to what? Let's calculate. Okay, that is nothing but magnitude of. We want to calculate the magnitude of this of F2 plus F3. We are going to do the vector sum of F2 and F3 and then calculate the magnitude of that. So, how do you do that? You basically go here to the parallelogram. For this parallelogram, you can see that this is 60 degree. Okay. So, hence you can clearly see that this is half of it, 30 degree, and this is basically 120 degree. Okay, and half of 120 degree is 60 degree. This is also 60 degree, and each one, this is again an equilateral triangle. If this one is an equilateral triangle, okay, then this length is same as this length, which is actually equal to again 3kq into capital Q by L square. No difference. However, if you look at the magnitude direction of that, that will be exactly opposite to F1. So we can say that F1 as a vector is actually equal to minus of F2 plus F3. As vectors, basically, if you do want to compare, magnitude wise they are equal. This is what is there. So that means we will say that F1 plus F2 plus F3 is equal to 0. That means net force at this point on capital Q is 0. So this is a way you learn to basically calculate how to calculate the net force due to various forces. So with the same technique, you can solve some of the problems which are given in the exercise, which are also of similar type, where you calculate the forces from various points and add them vectorially. Yeah. So now let's move on. So this is one of the examples to understand this. Now we are going to basically move to an important concept, pretty nice and interesting concept called as electric field. So we have covered, we have got some understanding of what is the electric charge. Okay. So we got some understanding of what electric charge and its properties, what kind of an animal that is. We figured out that. Okay. So electric charge over that we have done. Now we are moving to electric field. So what is this electric field? So when you actually look at uh, the Coulomb's law, what it tells you is this. So let's say we have a charge here, so capital Q, and here I have another charge. I'll give it as small q. Okay. Now what I want to find out is the force at point here. Okay, I'll call this point as say O and this point as P. I want to calculate the force on Q, which is positioned at P. Okay. How do I do it? I'm going to simply say it as, let us say this distance is r. R, we can say this is also a vector, r. So both are positive charges, so it will be in that direction. So we will say force is simply equal to K into capital Q into small q divided by r square into r cap. So this is Coulomb's law that we already know of. Now let's look at basically an interesting part here. Okay, what we do is we are going to write it slightly differently. We are going to write the first part of K Q into r square into r cap. This whole thing into Q we will write, and we call this whole thing as electric field. And denoted by E. So F is simply equal to Q into E. That means we can say that electric field can be written as F divided by Q vectorially. Okay, Q is scalar. So electric field is a vector which is in the direction of the force, but it is also basically its magnitude is as though you have put q is equal to 1. So, what does it mean? It means that we have this notion that whenever there is a charge here, okay, so if you put one charge here, it experiences a force. You have put one charge small q at a point P and it experiences a force. So, you may ask a question, what is there at P that it experiences a force? So, you will say, no, there is nothing at P, but there is a charge at capital Q. Now, it is possible that there are many charges everywhere else, where all of them put together will do something at point P, which will cause, whenever you put at the point P, it will cause it to repel. Okay. So, that thing which is there at point P is what we want to call as electric field. So, it is a kind of, we always say that if there is a charge, around the charge there is a certain field and we call it as electric field. So, this concept was actually introduced by Michael Faraday. It became a very interesting aspect. So, actually it does not really serve a great purpose in the case of electrostatics, because you could always talk about the force itself, electrostatic force itself. You do not need a field. Whereas, when you move a little forward into electromagnetic waves and all those places, it becomes very, very important. I will tell you in a minute why. Okay, here you see, I will just complete the definition. There is one tricky notion here, is saying that we call this Q, capital Q, as actually a source charge. Okay, this is a source charge, and small q we call it as a test charge. So, our idea is we want to basically find out the electric field of the source charge. Okay. To do so, we are going to take one test charge and keep it and find out the force on it. Then we take that force divided by the test charge q. That is what we call as electric field E. Some tricky situations arise here. Okay, like for example, practically if you want to do this, okay, what will happen is the moment you put this charge q, okay, now the q will experience a force because of capital Q, I agree, but at the same time it can also push capital Q to some other place, it can make it move and everything changes. It is just a practical difficulty. So, what we do is the measurement, for measurement sake we say that this actually better way is to keep small q as small as possible. Okay. So, what is the meaning of that? The meaning of that is we say E is nothing but limit small q tends to 0 f divided by q. So, that means you keep, see the force ultimately you get is very small, but q also is very small. When you divide that, you will get the actual value of E, which is not disturbed. I mean, it is one way of basically picturizing the testing aspect. And in fact, though it may sound strange, the other simple way is to hold the charge capital Q there itself through hold it in your hand as some other external force, so it does not move. Even then you can measure. Okay. So, now what is very important here is what are the basic features of this electric field. The electric field clearly for us is defined as force per unit positive charge. Force on unit positive charge at that point. Okay. What does it mean? That means that the electric field is not exactly same everywhere, in a sense that if you keep the positive charge here, you experience certain value of force. If you keep it somewhere else, you get another value of force, and that force may be different. And whenever you divide it by the suppose even here itself, if you put a different q, you will get a different force, but f by q, okay, will be same for that point. At every point, if you take f by q is same, which is our E. Okay, so the E is not going to change depending on the test charge. E is independent of the charge. It is independent of the test charge. It's simply dependent on the actual charge and the distance vector of that. Okay. So, and second important thing is the direction of E. What is the direction of the E? Okay. So, that is the second important point. You can very clearly see that if you put a unit positive charge wherever it goes, okay, that is the direction of E. In the sense that suppose if you had a positive charge here, okay, and at this point you put a unit positive charge, definitely it will be pushed out like this. So, hence E at this point is actually in this direction, in the same direction as the force on the unit positive charge. Hence, for all positive charges, you can see the direction of E around it is outwards. So, for point charges, okay, for point positive charges, E is outwards. Similarly, for negative point charges, E basically direction of the E is inwards. Okay. Now, these are some of the basic points about what are the typical characteristics of the electric field E. Okay. Now, once we get into this, we have to now ask a question on what about the electric field due to system of charges? Like we already saw, electric force, static force due to system of charges. This is similar, no different from that. So, we can actually, because this is also ultimately a electric field is nothing but the force on unit positive charge. So, it is also a force. So, it is just that charge is a unit charge, that is all. So, let us calculate the force or electric field due to basically multiple charges. Okay. So, instead of force on a charge, electric field due to multiple charges, or we can say system of charges. How do you calculate the electric field due to system? It's a very simple, straightforward way to do it. Let's just do it quickly. You have actually, let us say at this point P, this is the point P. I want to calculate electric field due to what charges? Let us say charge here and charge here and charge here, 3 charges. Okay, I can put any number of charges. So, this is charge 1, 2 and 3. So, now I am going to basically calculate the electric field here. How do I do it? As usual, I will call this as RP1. Okay. This is basically nothing. So, you can actually start from here, origin, connect to them for each one of them, and then RP1 is equal to RP minus R1, and that is this arrow. This is the relative basically position vector, and here you get actually RP2 and this is RP3. So, now if you have this let us say these are all positive charges for calculation purposes, for a practical purpose of writing the picture, but it as well holds for anything. So, this is P. So, now I am going to basically take here and write down the direction of E. This is E1, because if you say positive charge, okay, let us say this is Q1, this is Q2, this is Q3. Because of Q1, if you have a charge, you have a force that is basically exerted on unit positive charge, that would be equal to the E, which is like this, E1. Okay, and similarly, this is E2, and this is E3. E3. Now what do I want to do? I want to calculate E1 plus E2 plus E3. So superposition. Superposition of all this, addition, vector addition of all this will give me. So vector addition of E1 and E2 can be calculated by your parallelogram law here. This is E1 plus E2 and this can be again added to E3 and you will get the final E. So we can say E1 is equal to, what is E1? Is nothing but Q1 KQ1 divided by RP1 square into RP1 cap. So if it was a force, I would have multiplied with the charge which was here. Here there is no charge here now. We are just calculating the E. So that means that unit positive charge. If we keep whatever the force comes, that is E. So E definition is this. So we use E definition to write down the E. So similarly, you can write down E2 is equal to KQ2 divided by RP2 square into RP2 cap, unit vector. So if you add all those things, I3 and all those things, I am going to basically write down simply directly because you already once done. E is nothing but K into K divided by R. So I'll write it as K into sigma. So K is 1 by 4 pi epsilon naught. Okay. So sigma, I'll write it as 1 by 4 pi epsilon naught into Q. So look at I going from 1 to n. There are, let us say, n charges. So here it is 1, here it is 2 and 3, like that it goes. I'll say Qi, okay, divided by Rpi square into Rpi cap. This is nothing but the addition, adding all the E's together to get you the final electric field at that point. Now the beauty of the final electric field calculation is that while doing so, we actually did not care about what is the charge that we are going to put here. Because if you put a charge there and then we use Coulomb's law, it is the same thing. But now in this case, first we are going to basically calculate the electric field at this point. And you want to now find out the electric force. If I put a charge, let us say I want to put a charge here of, let us say, 3 coulombs and ask a question, what is the force acting on that? So that is simply equal to this E that you calculate into 3 coulombs and it will be in the same direction as the final E. So you can take at any point, find out the electric field and you can actually say, given a distribution of charges, you can actually talk about the electric field at various points. It is like, this is why it's called a field. It has different values at various points and all those values, if you know beforehand, then to calculate the force on any charge will be simply easy. You go to that point and find out what is the electric field, multiply that with the charges and the value of the charge that you are putting in there, and that will give you the electric field at that point. And even the direction is known because it is a vector field. It's called a vector field. The meaning of vector field is that if you take your 3-dimensional space, not just 2-dimensional space, 3-dimensional space, at every point in space, its value is defined. The value of E is defined. However, it is not just the magnitude. So at every point in space, small vector can be drawn. So that is basically the E at that point. So the whole of that is basically is nothing but our complete electric field, vector field. Okay, that's what we say. So this is basically our way of calculating at any one point electric field. So now what we are going to do is we will use this, okay, and do one simple problem. Okay. So take down the problem. So the problem is an electron an electron falls through a distance of 1.5 centimeter. An electron falls through a distance of 1.5 centimeter in a uniform electric field of magnitude 2 into 10 to the power of 4 newtons per coulomb. So an electron falls through a distance of, let's say, h is equal to 1.5 centimeter. The direction of the field is, so it's as per the figure, okay. The direction of the field is reversed, keeping its magnitude unchanged, and then a proton falls through the same distance. Compute the time of fall. So we have to compute the time of fall, and in each case, so that means we have to calculate TE, time for the electron to fall and time for the proton to fall, both of them, and compare them. Contrast the situation with that of a free fall under gravity. Okay, they have given a diagram here. The diagram goes like this. There are two plates here. Okay, I'm going to write it a little bigger. So two plates here, and if you happen to put in the first plate, on the top of the plate here, if you charge that only with negative and this one with positive, and we know that if you want to calculate a field at any point here, let us say I want to calculate the field at this point. Okay. So how do you calculate the field at that point? You're going to find out from here at this point basically to this positive charge, what is the distance, all that you have calculated for every charge and sum it up. Okay. And from this is all basically pushing that side, and these negative charges are also basically pulling it the other side. So if you put a unit positive charge, it will move up. So hence you can say the field is actually in this direction. This is how the field is. Field is like this. Field lines are like this. Okay. So now, if the field is like that, then what we are going to do is we are having an electron. So the electron is basically minus E, okay, the charge, and it is falling down. Why does it fall down? Because, not because of the gravity. The gravity also can pull it down, but I am now talking about falling down because it is attracted towards the positive charges. That means that if you have an electric field E, okay, electron always moves in the opposite direction of the electric field, always. So you can see electron moves in the opposite direction of the electric field. Whereas if you have similarly another scenario where this top plate is all positive, so that the electric field is reversed. Okay, so when the electric field is reversed means electric field looks like this. This is our E. So if there is a proton which is actually plus E and it falls here, proton actually always goes in the direction of the electric field. It's easy to understand why, because it is going towards the negative and away from the positive. Okay. So now the proton is falling, electron is falling. The question that we have to find out is for it to fall for 1.5 centimeters, both of them, what is the time taken? So it looks like a very complex problem, but actually if you see, it's not that complex. Okay, what we are going to find out is, if you know the acceleration, then we use our kinematics understanding to solve this. So what is the acceleration? So to know the acceleration, you need to know the force. So first let us calculate the force. Force on the electron, Fe. So if you want to really calculate the force on Coulomb's law, you think about it, you're going to basically take all these charges from there, everywhere you calculate what is the force and sum it up everything. It's a huge thing. Okay, that is already done. That is, for you it is given in the form of an electric field. So we know that the force is nothing but the charge. Always force is nothing but charge into E. That's all. So in this case, charge is E. So minus E actually into E. So if you want to calculate the magnitude of Fe, how much is that? They have given us actually the value of capital E, which is nothing but 2 into 10 power 4, and small e is actually nothing but the charge on the electron, which is nothing but 1.602 into 10 power minus 19. These two multiply, you get basically force. Okay, now once you get the force, you can actually now calculate acceleration of this, which is nothing but the force divided by the mass of that electron. Mass of the electron we actually studied in the last question to be basically 9.11 into 10 to the power of minus 31 kg, and here you get 1.602 into 10 power minus 19 into 2 into 10 power 4. So you can use your calculators and do this, and you will get basically an acceleration, okay, of about so you can calculate the acceleration. Okay, so once you calculate the acceleration, now you will actually substitute that acceleration in our formula, kinetic formula, called basically S is equal to ut plus half a t square, or h is equal to, assuming that it started falling from rest, u is equal to 0, correct? So nothing, then we will calculate t is equal to, Te will say square root of 2 into h by Ae. So Ae we have it here, h is given to us, which is 1.5 centimeters, which means basically 1.5 into 10 power minus 2 meters. If you substitute all that, you will get a Te, you do the calculation, and you will get a Te of 2.9 into 10 power minus 9 seconds. So it goes at such a high speed, in 2.9 10 power of minus 9 seconds, it reaches 1.5 centimeters. Okay, it's like nanoseconds, 2.599 nanoseconds it reaches. Okay, that means so much of acceleration it has. Similarly, you can actually calculate Tp, which is nothing but same as 2h divided by a p here, acceleration of p. So acceleration of p is nothing but, you get force. Okay, the force here is same, because force can, for Fe is also equal to Fp. Why? Because the charge on electron and charge on proton are same. Okay, only magnitude basically, okay, is equal to that, which is nothing but Fp here. Fp is same. So because of that, you can write the same value here. F divided by, you can have mp. So mp is nothing but, we have the value of mp to be, this is one, this is same as what was given there. I'll write it as F itself, and mp is the mass of the proton. Okay, mass of the proton is nothing but, this was also used in the earlier question. Okay, mass of the proton. So let me just check the mass of the proton for you. (1.67) into 10 to the power of minus 27 kg. If you substitute these values and compute it, so you will get the value of Tp as 1.3 into 10 to the power of minus 7 seconds. So this part of arithmetic, I want you to do it on your own. It's not very important though you may have to do it. But what is very important is to look at the final answer. Okay, the final answer here, the time taken for the electron to travel 1.5 centimeter is 2.9 nanoseconds. Okay, so let's write this also in nanoseconds. 1.13, let's multiply it by 100 and divide by 100. So 0.3 into 100 is 30. So 130 into 10 power 9 minus 9 seconds. So this is 2.9 nanoseconds. This is 130 nanoseconds, which means that proton is coming very, very slowly. So if I drop a proton and electron together on, let us say, gravitational force field, what will happen? So they are supposed to go together, exactly same acceleration, they will actually travel the same distance, because gravitational force is caused by the masses, and then the inertia of the masses, are basically accelerations, are proportional to the inverse of the masses. So the masses get cancelled there. Whereas here it is not the case. Here the force on each one of them are exactly same, because the charges being same, the force is same. And once the force is same, the acceleration depends now on F is equal to ma, or A is equal to F by m. In the case of a proton, since m being very high, the acceleration is slow and it slowly comes down. And in the case of a electron, it comes fast. You can actually calculate this value, the acceleration value, how much it is for a proton or a for a electron. You can see that for the proton, suppose if I calculate this value, okay, the acceleration value, it turns out to be basically about 1.9 into 10 to the power of 12 meters per second square. Can you see this? Generally, because of the gravitational force, the acceleration due to gravity will be how much? 9.8 meters per second square. Here you see 1.9 into 10 to the power of 12 meter per second square. So actually, you know what, when it is falling here, okay, this E is making it fall, but also the gravitational force is pulling it down. So we would have actually added the gravitational acceleration to the acceleration that is produced here, but we neglected. So were we justified in neglecting? Yes. This was just 9.8 that we did not take into consideration. This one was 1.9 10 power 12. If you add 9.8 to the 8, somewhere at the 12th digit it gets added. So it's okay to neglect that. So that means that gravitational force is so very less when compared to the electrical forces. So that is the understanding from this particular problem. Okay. So there is another problem, small problem that we can do. So take down the other problem. Let me dictate the problem for you. 2-point charges Q1 and Q2. 2-point charges Q1 and Q2 of magnitude plus 10 power 8 coulombs plus 10 power, not 10 power 8, it is 10 power minus 8 of magnitude plus 10 power minus 8 coulombs and minus 10 power minus 8 coulombs. Okay, we'll call it basically one of them as Q1, the other one is Q2. Okay, coulombs are placed 0.1 meters apart. Are placed 0.1 meters apart. Okay, and then calculate the electric fields at point A, B and C. Calculate the electric fields at points A, B and C. So, they have given a picture for that. So, this is Q1, Q2, this is A, this is B and this is C. So, this distance, this is L, this is 0.1 meters, this is 0.1 meters, this is 0.05 meters, this is 0.05 and this is 0.05. Okay. So, what is kept at Q1 is a plus charge, what is kept at Q2 is a minus charge, that is all is important. So, now first let us say we will calculate at A, okay, at A. So, we will say E at A, electric field at A. So, electric field at A can be calculated due to Q1 and due to Q2 and we have to add them. So, electric field at A is nothing but E at A due to 1 plus E at A due to 2. If you add them, you will get it. Now, let us understand what is the electric field at A due to Q1. So, this is plus and this point, it is always away from the point. That means, if you put a unit positive charge, where does it go? This side. So, this is nothing but E A1. From here, if you see, this is negative. For a negative, what happens? Positive charge actually gets attracted towards that, and hence E A2 is also in the same direction, and these both of them will have the exactly same magnitude because it is at a distance of 0.05. So, let us calculate that. Okay, EA1 is nothing but K into Q1 divided by 0.05 square plus. So, we have to now actually algebraically add. So, I am going to put it as EA magnitude. Both are in the same direction. So, we can simply add them. We do not need a vector to add that now. So, plus K Q2 divided by 0.05. They both are exactly same values. Q is here, K is 9 into 10 power 9 and Q is nothing but 10 power minus 8. Okay, and then I am going to basically put here. So, the direction I have taken the magnitude and I already considered the direction. It is both of them on this side only because this is pushing, this is pulling. So, they have to get added up, the magnitudes. So, I am going to write here 0.05 square. So, into 2. So, 2 because both are same exactly. So, what is the value of this? This value of this is basically nothing but 90 divided by 0.05 square is 0.0025, which is 25 into 10 power minus 4 into 2. Okay. So I am going to write this again as 180 into 10 power 4 divided by 25. So this is how much. So if you take 100 out of this, 25 fours are. Okay. So what is 18 fours are? So there is a 720. So I will say 720 into 10 power 2. Okay. 720 into 10 power 2 as nothing but 7.2 into 10 power 4 newtons. Sorry, this is nothing but newtons per coulomb. This is our EA. So if you want to calculate EB, let us look at EB now. Okay. What will happen to EB? Again, magnitude of EB, if you see, okay, at the point B, this is basically pushing it away, okay, and this is pulling it this side, but it is weaker. Okay, ultimately, if you see why it is weaker, it is farther, so it is weaker. So ultimately, it is on this side. Okay, this minus that. So I will say magnitude of EB is simply equal to, okay, KQ1 by 0.05 square minus, in this direction it is there, KQ1 divided by, the distance is how much? 0.05 into 3, okay, square from here to here. So I am taking this minus this. So that is what basically a resultant will be. So this is how much? This is nothing but 3.6 into. So let's anyway calculate this. Okay, when you calculate this, you will actually get a value of let us say 3.2 into 10 power 4. Okay. EB is correct. 3.2 into 10 power 4 newtons per coulomb. So please go ahead and calculate. It is a straightforward calculation. Let me just check whether I have done anything wrong. So this actually not turns out to be 7 point, which is nothing but EA is nothing but 7.2, correct. 7.2, sorry, it's correct. And EB turns out to be nothing but 3.2, correct. That is also my calculation is correct, into 10 power 4 newtons per coulomb. So however, if you calculate actually EC, okay, the EC is a little tricky. Why is it tricky? Because in this here the direction is like this. This is EC because of 1. This is the direction because it is attracted here. This is EC because of 2. So you can actually calculate this and you can figure out that this length will actually be equal to the same length of this. So you using it right angle and using a equilateral triangle, you can calculate. You can calculate one of them and this length will be same as that. So that will turn out to be for us as an outcome is nothing but 9 into 10 to the power of 3 newtons per coulomb. So this is how you can actually calculate E at various places. Just an example to calculate E based on different kind of different charges distributed as a system of charges. Okay. So that basically brings us to the understanding of handling multiple charges and also the electric field due to them. So the next class, next session, we are going to look at start with basically looking at what is the meaning of electrical field lines and what is the electrical flux, and then we'll move on to understand electrical dipole and all these things. Thank you.